kinematics. Now, what we introduced was this idea of theta, the angle relative to the x-axis, omega, how fast that's changing, and alpha, how fast is omega changing? Are you accelerating as you change that angle? And this relates back to linear equations, the kinematic equations, and we probably remember what some of those are. So for instance, x final equals x initial plus vx initial times t plus 1/2 a sub x t squared. Okay, hopefully that one looks familiar. That might even be burned into your brain by now. We can put this into rotational form simply by changing variables. So xf becomes theta f. xi becomes theta I. Vxi becomes omega I. We keep the same time. A sub x becomes alpha, and then we have t squared. So you in fact already know this equation right here. You are just changing variables to go to rotational form. It's all the same equations. Okay, so that's one of them. Let's see how another one works out. Okay, so for instance, VF equals VI plus AT. We remember that one. This becomes omega F. This becomes omega I. This becomes alpha, and we keep the same T. So there's another kinematic equation for rotational motion. And we have a couple more, right? Another one is VF squared equals VI squared plus 2AXF minus XI. We can write this one in rotational motion. And this becomes omega F squared equals omega I squared plus 2 alpha theta F minus theta I. And then finally, our last equation is this one, xf equals xi plus 1/2 vi plus vf times t. And that equation, you can guess what it is now. Theta f equals theta I plus 1/2 omega I plus omega f times t. And that becomes our last kinematic equation for rotational motion. So, like we had in the linear case, 4 kinematic equations, we now have in the rotational case 4 kinematic equations. But there's an important caveat. Rotational kinematics, all these equations, only work if alpha is a constant. Okay? If alpha is not a constant as a function of time, then these equations don't work. Now, a constant could mean alpha equals 0, but it just means that it can't change as a function of time. Okay? You have to look at regions of constant alpha. Okay, so with this in mind, let's take a look at an example problem. So let's look at a washing machine. And let's think about the rotational motion during a washing machine cycle. So we all know what a washing machine looks like. It looks like this. Okay, in there is a cylinder, has a big drum in there, and that cylinder spins around in a circle. Okay, and now the washing machine has regions of time where it is spinning up, it's accelerating angularly. It has regions of time where it is moving at constant omega. And it has regions of time where it is slowing down. Okay? So if we think about alpha for these different regions, what can we say? Well, alpha is positive in that region, alpha is 0 in that region, and alpha is a negative constant in that region. Okay? And let's give you some values and let's figure out something about this motion. Let's say that omega I on the way up is 0. And let's say that omega final is 5 revolutions per second, okay, while it's spinning up. 5 revolutions per second, that is not really the right units, but we can convert it to the right units because we know that 1 revolution is equal to 2 pi radians. Okay, and so this last little bit becomes 10 pi radians per second. Okay, so we've got some information here. We want to figure out something about the motion. What do? Well, we can use the kinematic equations.